the YouTube thing, whatever. So okay.
Yeah, we are live now.
Okay. Yeah. So I guess I'll start sharing my screen. So okay, are there people here with mobile phones, like on their mobile phones, because they had some trouble last time with the
Yes,
chat
sir.
thing? Okay. So like, do I need to share my screen to show the problem set to people? Because last time there was an issue. So has everyone received the problem set and is able to access it?
Sir, where
Yes,
can we
sir.
get it?
Yes, sir.
Okay, okay, fine. So okay, I guess then we can start. So yeah,
Sir,
yeah,
problem set.
yeah, it's in the
Sir,
chat. Sorry, what?
sir, I'm not able to see the problem set.
Yeah, so then you must be on your mobile phone. So okay, I'll just
Yes, sir.
okay. So what I'll do is I'll just share my screen. Right. So then okay. Okay, are people able to see the problems now?
Yes,
I'll
sir.
just zoom in,
Yes,
and
sir.
maybe you can
Yes,
take a
sir.
screenshot now and
Yes.
then refer to that as we go along. So um, this is okay. Like, people have screenshot this. So yeah,
Yes,
just
sir.
let. Okay, cool. So I'll just stop sharing this now. All right. Hope everybody has got it now.
So, sir, can you share it once again, sir?
Okay. Yeah. Okay, sure. Yeah. Uh, uh, shall I zoom in more? Yeah. Okay.
Yes, sir, done.
Okay. Cool. All right. So all right. So yeah, I guess we can start. Okay. So so people can work on whatever problems they choose. All right. So like, the first problem is kind of interesting. It's a little bit tough, but it's interesting. I discussed the first problem yesterday only, so I guess I'll do something else today. Um, yeah. So, like, is there any particular problem people would like me to do? Anything that
So
by
like
the way,
the solution to the solution to the sixth question will be fx equal to x, I think.
yeah, sixth problem you mean? Actually, yes. I mean, minus x also works, right? Because
Yes, sir, there are too many solutions, but I have got only one. Actually, I'm
yeah,
proceeding on it. Okay.
yeah, it's fine. So like, is there any particular problem people would like me to discuss? Or I can just like go along with like something random. I was
So number 1 and 3.
okay, yeah. Number one is nice. Oh yeah, actually three is also nice. So yeah, three is a
Sir,
classic problem. Yeah.
sir, I'm not able to see the screen.
Uh, are people able to see the screen? Or like, because it's saying that it's sharing. So is everybody else able to see the screen?
Yes, sir.
Yes, sir.
Okay. Yeah, I'm not sure what I can do to help the person who's having trouble. The issue is not on my end. So okay. Um, Anyway, so okay, I guess I'll start with three. Then we can go to first. So all right, right. So the thing is, if suppose you have your p to be some a square plus b square, right? So then it's obvious that it will take non-negative values at all points, all real points, right? So the thing is, we just essentially the problem statement is saying that this goes the other way around as well. Yeah. So right. So the thing is, if you so this is kind of simple really. So if you take px, so you can just uh, factor out the real roots um, with something like this, and then what you have here are just the complex roots, right? Now what you do is okay, is the brightness okay with everyone? Because I think I should maybe, yeah. So, yeah, I
Hello,
think
sir. Can you please share the screen once again?
okay, okay. uh, I'll
Sir,
just
actually, I got disconnected in between.
yeah, it's okay. So um is this okay now? Hmm?
Sir, I'm asking about the problem set.
Oh, okay, okay, yeah, 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 sure, okay. Oh, you can't access the chat, is it? Okay. uh I see. So yeah, all right. Okay, so yeah, just take that.
Yes, sir. Done. Thank you very much.
Okay. Okay, so I'll share the screen again. All right. Everything fine now?
Yes, sir.
Okay. So, okay, as I was saying, so we can kind of separate out the real roots and look at what happens in the complex part. Well, well, not really the complex part, the root with the part with complex roots. So, so the thing is, if alpha plus I beta is a complex root, then its conjugate alpha minus I beta will also be a complex root. This is much we know. If beta is not equal to zero. So the thing is, you have one factor coming in like this, and okay, so you obviously will have a constant factor, lambda. But the thing is, you can actually ignore lambda in this case because lambda has to be positive. Otherwise, px cannot continue to be non-negative as x goes to infinity, right? I mean, if lambda were to be negative, it will go to minus infinity. So yeah, so then you have something like this. So then this particular thing will be products of these units like these. Now this is just x minus alpha square plus beta square. This particular thing is positive, and also you have this particular identity. Yeah, this identity kind of comes in hand a lot. So nice thing to see. Yeah. So what this says is that if you take two polynomial expressions or even numbers, or actually anything for that matter, that can be represented as sum of two squares, and you take another one which is also sum of two squares, then you can the product, and then the product could actually also be represented as sum of two squares. So so if you look at the complex part, right? So it's just products of it's just product of things like these. So then this product is also sum of two squares. Is, I mean, you can just inductively argue that. So the thing is, you will have that this particular thing is some a square, a1 square plus b1 square. Everything okay up till now? Okay. So now the thing is, you have lambda is greater than zero as well. So you know that root lambda is a real number. So 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 you actually have that px is some x minus alpha power r1. Okay, yeah, maybe alpha is kind of unfortunate. So okay, gamma 1 x minus gamma m power rn with some a1 square plus b1 square. Now the thing is, if you show that all these gamma i's are even, then these become squares as well. So you can just absorb them into a1 and b1, and then you get p to be some a square plus b square. Does this make sense so far? Okay. So yeah, if at any moment you feel like I'm going too fast, just let me know. So okay. So now we have reduced this problem to showing that divided, need to show. All right. So so suppose for contradiction's sake, we have that some particular root gamma has odd multiplicity in P. So we'll have something like this going on. If we look at the graph of P, right? So it will obviously touch the x-axis at gamma, and the thing is, P will change sign around gamma, is what the claim is. So the thing is, if you have your root gamma and then you have these other roots over here, and then you have these other real roots over here. The thing is, you can find a small enough epsilon such that there is no root of gamma in this particular interval. You can always manage that because there are finitely many roots, so you can just take epsilon to be small enough to avoid all those roots. Right. So yes. All right. All right. Okay. So now we need to. So claim is p x minus. Right. So the thing is, you can write your px as x. Sorry. Um, so x minus gamma power whatever you had r times some p1 x, where p1 does not vanish on plus epsilon. Right. Now, since P1 is a polynomial, right? So for the polynomial to change signs, it has to have a root. So for a polynomial to actually change signs in an interval, it has to have a root in that interval. So P1 does not have a root in this interval, so P1 will never change signs. So P1 x times P gamma is greater than 0 for all x. Okay, let's just for sake, for notation sake, let's just call this interval G. So for all x in G. All right. So sorry, P1. Yeah. So now we just need to show that this x minus gamma power r changes signs. If the so the thing is, P1x has a constant sign. It is either consistently negative all through J, or it is consistently positive all through J. So if you just show that this particular factor changes signs, then we are done. Now the thing is, that's kind of quite easy to see, right? Because you have just x minus gamma power r, and r is odd, so you can just take x minus gamma whole squared power some m times x minus gamma, and this is all consistently non-negative and is vanishing only at gamma, so it will be positive at all is greater than 0 for all x in J minus gamma. And the thing is, this is going to change signs on either side of gamma. So you just have that. Now the thing is, you can't have P changing signs, right? P can never be a negative. So you get your contradiction over there. So you just have that this R is always even. So this thing is a square, and you can, as I mentioned, absorb it into A1 and B1.
So can you give a bit of summary like that for this question?
Yeah. Okay. So the thing that actually is being crucially used over here is this identity. And the fact that if you have complex roots, they appear in conjugate pairs. So their product will be actually will be a sum of two squares. So the thing is, the factor that the largest factor with only complex roots becomes a sum of two squares because of this identity, right? So you can just take, it's a finite product of complex roots. So it looks something like this, and the constant itself is a positive thing. So yeah, its root is real. So it also gets absorbed into this particular sum of squares, and so you just have that px is just some real roots, is a is a is a product of some function, is a product of a polynomial that can be represented as sum of two squares and some real roots added to it. So yeah, and then we just showed that these real roots must appear with even multiplicities. So then they can be absorbed into the squares, and we get sum of two squares in the end. Is that okay?
Sir, can you explain why you do gamma and epsilon?
Right. Okay. So this was actually to show that if gamma is at all a root of a real root of p, then gamma must appear with even multiplicity. Now, how I go about this is I basically pick a small interval around gamma, an open interval. So there are finitely many roots, right? Real roots. There are finitely many. So you can choose a small enough epsilon such that there is no other root of p in this particular interval. That is gamma minus epsilon, comma gamma plus epsilon. Is everybody clear why we can do this? Okay. Right. Now you have that j is an interval where the only root of p is gamma. Now, if you factor out gamma out of p, and suppose you remain with p1. Now, p1 does not vanish at any point in this particular interval. So p1 cannot change signs, because to change signs, it has to go through zero, right? Because like a polynomial function is a continuous function. So it can't be positive and negative in the interval without going through zero. So right. So the thing is, so you just have that p1 is either consistently positive or consistently negative. To show that p changes signs as it passes, as it passes through gamma, you need to show. So you just need to ensure that this particular thing will change signs. So now you ensure this by using the fact that r is odd. So the thing is, if r is odd, you can just factor out the even part, and that will be a square to the power something, and that will obviously be positive. And you'll have this loner, and this loner will actually change signs. So which is why you get that p changes signs across gamma. But the thing is, we were given that p is non-negative across all real numbers. So that's a contradiction. So you just have that all the real roots appear with even multiplicities, and you can just absorb them into the sum of squares that you had.
Okay, sir.
Any other questions? All right. So people were asking for 1 and 3.
So,
Yeah.
sir, in this question, can you explain the very last part that you said when you separated that x minus gamma?
Right. Okay. Yeah, I'll do that. Yeah, just a second. All right. So okay. Did you get the part where we have reduced the problem to showing that so gamma must have even multiplicity? Like, did you get until that part?
Yes, sir.
Okay. Right. So essentially, we're just trying to show that gamma, every real root has an even multiplicity. So the negation of that statement is some root must have odd multiplicity. So suppose gamma is one such real root that has odd multiplicity. So now the thing is, we choose an epsilon small enough, positive, such that this particular interval, this open interval, has no other roots of p. Okay, we can do that. since P has finitely many real roots. So is that fine with everyone?
Yes, sir.
Okay. Right. Now what we do is, so then what we do is, so suppose now we factor out gamma completely out of P, okay? So we just have something like x minus gamma power r and some P1x, where P1x has no roots in the given interval. Now the thing is, P1x is a real polynomial, right? And it has no roots in the given interval, so it has a consistent sign all through this interval. Is that clear? Why that's the case? Okay.
Yes, sir.
That's clear. See, because P1 is a continuous function, right? It's a polynomial. Now, the thing is, for it to change signs, it has to go through 0. But the thing is, it has no roots in this interval, so it can't go through 0. So it has to have a consistent sign all through this interval. Okay. Now, we just need to show that x minus gamma power r changes signs, but the thing is, r is odd, so that's kind of easy to see. Like, because like the thing is, if you just shift your origin to gamma, so you just have x power r where r is odd, so that is well known that it will have be negative. Since r is odd, it will be negative on the negative side and positive on the positive side. So yeah, there you have it.
Yes,
Sir.
understood.
Sir.
Yeah.
Sir, if Px does not have any non-real root, then one of A and B has to be 0. Means either
that's fine. That's fine.
Sir, but we need to ensure that AB must be non-zero polynomial.
No. That's not part of the problem statement, right? The problem statement is you just need to find A and B in A and B are just like supposed to be polynomial with real coefficients. They might be 0, they might not be 0. It's fine. Like suppose you have your suppose you have x square, the polynomial x square, for example. So it can't be.
Then it will be x square plus 0 square, but that is trivial if there are no non
so that's
real roots.
That's fine. I mean, the problem statement doesn't ask you to find non-zero solutions, right? I mean, even if suppose you get it a square, you can just write it as a square by 2 plus a square by 2, if that bothers you. So just a by root 2 whole square plus a by root 2 whole square.
Sir.
Yeah.
So in question number 2, sir, what is tau of n?
Right. So tau of n is supposed to be the number of factors of n, and sigma n is the sum of factors of n, including n.
Sir, on account of school exam, I was late in joining the class. Would you please show the questions which you are doing?
Right. So are you on a mobile phone or some other device?
Sir, I'm on a laptop.
Okay. So then I'll just send the file again. So that should be fine. Okay. I have sent the problem set to chat. You can download it from there. So did you get it? You got it?
Yes, sir, I got it.
Okay, cool. All right. Okay. So then people were asking for 1, is it? Okay. Yeah, I guess I could discuss 1. Actually, the thing is, I discussed 1 yesterday. So since these are like the other sessions are available to you, also I would. I mean, it might be a waste of time to discuss 1 again. So I would discuss some other problem, if that's okay. Yeah. All right. So
which questions you already
sir,
discussed?
can you just give a hint about problem 1?
Okay. So the hint about problem 1. So as usual, you should start by noticing some basic properties of f, whether f is injective or surjective or unbounded, bounded, some things like that. Where you will actually find that f is injective and therefore unbounded. You need to use that. Okay, the first thing that you should do is guess the solution. So can people like give me some possible answers?
F of
If
x
x
equal to
equals to
x.
a squared x,
Yes. So fx equals a squared x. Fx equal to x is indeed a solution if you put a equal to 1 or minus 1 over there. Fx equal to a square x, where a is any integer, is the, I mean, not any integer, any non-zero integer, is the entire solution class. So yeah, now you have the answer, and you just have to kind of drive your intuition in a way to reach a proof. Uh, so yeah, okay. Yeah, so I guess the source is mentioned. You guys can check out the solution over there. And if you want further elaboration on the solution, then you can just uh, look at yesterday's session. So yeah.
Sir, can you
Uh,
do number 4?
So can you
okay.
do?
Yeah. Yeah. Somebody else was saying something. Okay. So I guess yeah. So I can do 4. Right. So yeah, it's for the first strategy about, okay, what's going on. Yeah. So first strategy for going about these problems is kind of plugging in values and hoping that something clicks. So actually, if you plug in m comma 1, right, so then you actually get that fm is equal to m times gcd fm comma f1. Okay. So the thing is, then you have something really nice at your hand. So okay, actually some guesses would be nice. So can people give me some guesses for what f could be?
Fm equal to m.
Yes,
Fm equals kx for any non-negative k.
Yes, that is actually true. So fx equals kx is a solution. Right. So see, guessing is important because that actually would help you shape your arguments and your intuition as you go along the solution. So yeah, you should always have some guess in mind, and it should be as broad as possible. So okay, so then you have something like this. So you just have that fm is equal to m times gm for some function g n to n, right? So and you also have that gm divides g1. Right, and this just implies G1 is equal to F1. So for all m. Now you just need to show that this GM is a constant function, right? That you just need to show that GM needs to be equal to G1 for all m. So right. So
Sir,
you, yeah.
so can you explain so why G divides G1?
Right. So G1 is just F1, right? Uh, because of this, how we define G.
No. Yes, sir.
And now G1 is just the GCD of FM and F1. So it's a factor.
Yes, sir.
Okay. Right. So you just need to show the other way around. All right. Okay. So now let's see. So f of mn is just m times n times gmn, and so the equation, the function equation now becomes mn gmn. So this just becomes gcd m comma n. So you didn't have the gcd m comma n.
Sir, can you please tell why did you cancel mn with LCM of mn where
No,
which
I
is
didn't
not
cancel it. I just kind of divided and wrote GCD over here. Yeah, yeah. It's not. I'm not canceling. I'm dividing it. Yeah. So this is what it reduces to. Hence, you have the GCD because I divided with it. So this is what the equation reduces to right now. Is that okay?
Yes, sir.
Oh, yeah. Plugging m and m will actually, so yeah, if you plug m comma m, you get something like f of m square is equal to m times f of m. Yeah, that's absolutely correct. So this actually will give you that gm square is equal to gm. Oh, yeah. This will actually give you that. So yeah, somebody in chat pointed out that I should do that. I should consider doing that. Yeah. So yeah, that's a nice observation. Like it's always nice to have these observations at hand. Um, like okay. Hmm. So let's see.
Sir,
Hmm.
sir, from there we got that GM divides G of 1, where G of 1 is a constant. And sir, we can say that G1 not equal to 0 because this function is ranging on a natural numbers. So GM, if it is not a constant function, it divides G1 for infinitely many numbers. So we can say that GM must be a constant function. From there,
That's not entirely true, right? I mean, it can be oscillating. Like so, if you take this sequence 1 2 1 2 1 2, every term of this divides 2, but it's not a constant function, right? I mean, what you can say is that GM will take one particular value infinitely many times. That's all you can say. Yeah, that was clear, right? I mean, not every bounded sequence is constant. Uh, if we have some like if we have some increasing non-increasing or non-decreasing condition, then we can always say that it will be eventually constant. Yeah. Okay. All right. So we kind of have this thing, which is important. So okay. Um, Now actually we can scale f if we need to just assume g1 is 1.
Think I can do it because if I put m equal to 1, it turns out that g of n divides g of 1. Isn't that
Yeah,
correct?
that we had, right? That we already had. So yeah, I mean we already had that condition that gm divides g1. We are trying to look for the other way.
Oh, sorry.
Yeah. Got it. So yeah, I guess people can think about this for a little bit and then maybe.
Sir, can you write the previous result once again so we can see it at a glance?
Which one?
You said that GM divides G1. That one.
Okay, yeah. So yeah, GM is equal to GCD F1 FM, F1
Okay, sir.
comma G1. Yeah, feel free to jump in if you think of something.
Sir, can we take M to be Mn and N to be 1? If that helps.
Okay,
Then we
yeah,
can
that's an interesting thing to suggest. So, so when you plug in just mn comma 1, right, you just get that gm, you just get the definition of gm. You just get that gm and divides g1. That's it. Okay.
Sir,
we can take an m equals to p to the power m, q to the power n. Then
Okay.
like the product, then we can write a product as two types, like p to the power m and q to the power n, and p to the power m minus 1 times q and p times q to the power n minus 1. Then we'll get the two GCDs. So like by this frame I prove that uh, f like like we got already m divides fm. Now we can prove that the highest power of, like the highest power that is in fm is m.
Um, that's not. That's not entirely true, right? I mean, it could have. I mean, K might be contributing some of the prime factors as well.
Yes, no, like I just had this idea and
Okay, okay.
somewhere.
So let's try this then. So you were suggesting that I put m as p power m p power alpha minus 1 times q, and n as q power beta minus 1 times p. Is that so?
Yes, sir.
Okay. So okay, let's just work this. So GCD of these is just p times q. Uh, so you have g p power alpha q power beta, and then you have GCD. Okay, so we can just cancel out PQ out of here, so you just get P power alpha minus 2 and Q power beta minus 2. Right. Uh, yeah, the thing is, you don't know how much of P can be coming out from here, right? And how much of Q might be coming out of here. Yeah, what do you do beyond this?
Yes, sir.
So what is how should we go about beyond this?
So I had really thought it out, but like there is one like the LCM one, like PRQ are odd primes if you assume. Then there's p to the power m and q to the power n in one, and p to the power m minus 1 and q to the power n minus 1 in the other. Therefore, out of the GCD, there must be an extra PQ power which does not come out of the other GCD term.
Okay. It will come out of the GCD term, and one will come out of that thing, na? One will come out of LCM, and other one will come out of GCD. So in the end, it will just balance out, right?
Sir, can we assume that g of m is a natural function from natural to
Yeah.
natural?
You can assume that. I mean, it's Fm by m, so it is the ratio of two natural numbers, which is an integer.
So we can take one of m or n to be a prime if that helps.
Okay,
Sir, how do
so
you know the
if you
ratio?
take one of them to be prime,
Sir,
what happens then?
sir,
So
sir, how do you assume that the ratio of two natural numbers will be an integer?
right. So if you plug in m comma 1 in the initial functional equation, you get that Fm is m times something.
Yeah.
That something is GCD of Fm and F1.
Okay.
Yeah. So with that's where you get that m divides Fm. Yeah, this is actually kind of weird because I tried looking up the source that I've mentioned, and it's not there right now, which is kind of weird. It was there when I was making the problem set.
Sir, I have done question number 5.
Okay.
Sir, I have
5.
done it like in the way that like the function that maps from n to n. It can be either increasing or it can be either constant as it's mapped from the natural numbers.
Wait. I mean, it could be oscillating, right? So.
Yes, sir. But the fact is, like when we took that it is increasing, then it leads to contradiction in the case because
Right.
it's not injective, sir. It's surjective.
Well, it's not surjective. the problem statement says it's not surjective. So
Sir,
Yes, sir.
it's definitely not injective, but it's not surjective
Yes, sir.
either.
sir,
Sir, but that should be a constant one.
Sorry, what?
Sir,
Yeah,
but
yeah,
that should be a constant one.
yeah. That's the problem statement. So
Yes, sir.
how do you show that? I mean, the thing is,
number
you
5.
just have that. Yeah.
Sir,
Sorry, somebody was saying something.
Yes, sir. Sir, I showed that for all n greater than equal to n naught, it
Huh?
is f of n equal to 1.
Yes,
Okay.
yes.
And then for I am taking suppose a number f of n naught minus k. That is,
Huh?
I am claiming that suppose it is greater than 1.
Huh?
And then I am putting f of n naught minus k equal to c. And then I am putting that n equal to n naught minus k in the principal equation. So I am getting that f of n naught minus k plus c, that is greater than 1.
Huh.
Now I know that for all n greater than equal to n naught, f of n equal to 1. So
Yeah.
that should be c minus k, that should be less than equal to c minus k, that should be less than equal to 0. So c is less than equal to k. So f of n naught minus k is less than equal to k. So now I am putting k equal to 1. So f of n naught minus 1 is less than equal to 1. So f of n naught minus 1 equal to 1 because it is a natural number function. So now I am doing induction on it. So I am getting f of n naught minus k for all k belongs to n. F of n naught minus k equal to 1. So it is a constant function.
Right. I guess a simpler way to see this is kind of as follows. So, absolutely. So if you just keep on plugging in and not, I mean, if you plug in and not and then keep on applying induction, you'll just get that f is
Excuse me,
consistently
sir.
1. Yeah. Sorry. What? Yeah.
Sir, can we, in the fourth number, can the function be f of x equal to x?
Yeah. The thing is, what we are aiming for is to show that fx is of form kx for some any natural number k, right? So that includes the identity function.
Okay, sir.
Yeah. Right. So. So what I was saying, so the thing is, if you keep on applying induction after n, you'll get that f is consistently 1 from n naught. Now the thing is, suppose f is not 1 somewhere, you can, I mean, it's easy to see that the thing is, suppose f is equal to something. So suppose fm is equal to c. Then you can find a natural number n which is bigger than m such that fn is equal to c. You can do that because you can take n to be m plus fm, and fm is a natural number, so m plus fm will be greater than m. So the thing is, you can kind of keep on pushing this, and you can always eventually find a natural number that is greater than n naught, that comes in, that also has its f equal to that particular c, and that's where you get your contradiction. Okay, I think my screen just stopped sharing. I'll just share it back. All right. Okay. Yeah. Just hold on a second. I'll kind of make sure that I have cited the right source for this problem, because I'm not able to find this problem over there.
Sir,
Yeah.
so we can take mn and such that f m and f of n are consecutive integers so that DCT can be 1.
Wait, so what you're choosing is n to be m plus 1, is it? Okay, so okay, that's an interesting approach. So you just put n to be m plus 1. Okay, So if you put that, then you just have g of m times m plus 1 is equal to GCD mgm m plus 1 gm plus 1. Right. Now, since m and m plus 1 are co-prime, it will just be GCD gm comma m plus 1 times, okay, not times, I would say. Is it times? Yeah, I guess it is. It is times that. M comma gm plus 1. Is that something that's happening? Yes, yes, it is. So yeah, we have something like this going on. Yeah. Yeah. What do you do beyond this? Yeah. So, uh, yeah. What was your idea beyond this? Okay. Yeah. I guess. Yeah. I don't think this would lead to some. Other thing. Yeah. I think I have found the source. Oh, yeah, sorry, sorry. It's Korea National 2013. Yeah, that is, yeah, my bad. It's not 2015, it's from 2013. Yeah, anyway. Right. All right. So, okay. So, okay. Right. Right. So, yeah. So, actually, going. So, this is the solution is kind of because of the user in that thread. So you have that GM is equal to GMGM, comma G1, right? Um, so I mean, you obviously have. All right. So now suppose if G1 divides M, right, for some M in N, then what you have is that GM is equal to G1 for all those M, right?
So how?
Right. So the thing is, this is GCD, right, of MGM and G1. So if this has a G1 factor over here, the GCD is exactly equal to G1. Yeah, this is obviously assuming that G1 divides M.
Okay, sir.
Yeah, yeah, yeah. Okay. So yeah. Now uh, you had something like G of Mn times. Yeah, maybe I'll just copy it up. Right. Yeah. So okay. Okay. How to? Okay. Yeah. Yeah. So we have this going on. Now suppose yeah, so mm, right, so okay, right, let me think. So you all, we had this thing. So now suppose G1 is dividing M, right? This implies G1 divides Mn. This implies G1 is equal to Gmn, right? um So we have G1 is dividing GCD of MGM and NGM. This implies G1 divides NGM. Right. Now again, since this is true and Gn is equal to GCD of NGN, comma G1, this is equal to G1 for all n. Right. Yeah. Yeah. This was a nice argument. So, yeah, this is obviously not mine, as you guys can see. So, what he's doing is, as you can see over here. So, uh, if we suppose that if we plug in just n equal to 1 over here, we get that gm is equal to gcd mgm and g1. Now, if suppose g1 is dividing m, then we have that g1 is a factor in here, so the gcd becomes equal to g1. So we have something like this going on over here, as we had claimed over here. Now what happens is, so we have natural numbers m such that gm is equal to g1 now, and that is true for all m's such that g1 divides m. Now you choose your n arbitrarily, and you just have that g1 divides mn, and this particular statement implies that g1 is equal to gmn. Now again, you have that since so if you so this just becomes equal to g1, right? So you have that g1 divides this thing. Now of course g1 divides mgm because g1 divides n, but what you get out of this is that g1 divides ngn for any natural number n. So yeah, this is what you have. Now again, if you plug it back into this equation that you had, so what you'll get is that GCD of, so Gn is equal to GCD of this, and this is just equal to G1. So Gn is equal to G1 for all natural numbers n. Okay. Okay, so somebody is suggesting that since gx was equal to gx square, we can kind of keep on doing this. So gx becomes equal to gx square, gx power 4, gx power 2k. Now that person is also suggesting that we kind of do it the reverse way. But the issue with this is that root x might not be a natural number, and g is defined just on natural numbers. So yeah, you can't plug in root x. It has to you have to, yeah, this is actually something worth mentioning. So while solving this problems about functions, you need to always ensure that whatever entry you are plugging in is indeed in that uh, domain. So yeah, you can't just plug in root x unless you know unless you know x to be a perfect square. You can't plug in root x if the domain is natural numbers or integers or rationals even. So yeah, there's that. Is there any issue with this proof? Yeah, again, sorry. So this is actually Korean national from 2013, not 2015. Yeah.
Sir, in the last question, I've got the criteria for MN0, but less than FN0, I'm not getting it. So please explain it.
Wait, so could you repeat your question?
Like in the question number 6, I proved that for all natural numbers greater than, which is like n naught, we are getting that function as 1, but less than n
Okay,
naught,
the
I'm
last
not
one.
getting. Yes,
Right. Okay, so that's problem number 5. The not the last one. Anyway, so right. So the thing is, if you have that fx is equal to 1 for all x beyond n naught, right? Now you just need to show that given. So you need to now extend this to all natural numbers. So suppose you have some natural number. Okay, I think I should write this down. So okay, we have fx equal to 1 for all x greater than equal to n naught. Okay. Now you have that f of n plus fn is equal to fn for all n in n. So suppose there exists k belongs to n such that f of k is equal to c. Okay. Now the thing is, if you look at this particular set, right, S to be x such that x belongs to n, comma, f of x is equal to c. You have to prove, you can prove this. S is unbounded. Okay. Try showing this. Once you have that if S is unbounded, you get your contradiction, right? Because f beyond n naught is consistently 1. So S cannot be unbounded. Now, how to show that S is unbounded is, so suppose n is in S. This implies n plus fn is in S, because f of n plus fn is equal to fn. Now n plus fn is strictly greater than n. So you can keep on repeating this process until you go beyond n naught. Or actually, you can keep on repeating this process to show that that S is unbounded. So what this functional equation without the restriction of fn naught equal to 1 implies is that f if it takes a value, it takes that value infinitely many times. Yeah. So I hope this was clear.
Yes, sir. Yes, sir.
Right. Any other questions?
So can you give a hint for number 2?
Number 2, right. Okay. The hint is that there are actually no such natural numbers n, and you have to kind of make an argument with the least prime factor dividing 2 power sigma n minus 1 and least prime factor dividing tau. You kind of have to show that the least prime factor that divides 2 power sigma n minus 1 is smaller than the least prime factor of tau n. And that will involve some arguments using order. So yeah, actually, I should ask this. So are people here familiar with the notion of order and primitive roots, things like that? Okay. So if you are not familiar with it, I would suggest that you look those things up. Those.
So order means like a power d is congruent to 1 modulo n, like the least d such. It's like the order.
Yes, 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 yes,
Okay.
yes. Yeah. So I would suggest that.
Sir, sir,
Can
it
you
is
please
sufficient.
Sorry, what?
Sir, it is sufficient to show that sigma n and p minus 1 is co-prime, where p is the least power dividing that tau n.
Okay, so suppose p is the least prime dividing tau n, you need to show that p and
sigma n and p minus 1 is co-prime, because p divides 2 power sigma n minus 1 and p also divides 2 power p minus 1 minus 1.
Right. Yeah.
So
yeah.
their GCD is basically 2 power GCD of p minus 1 and sigma n minus 1. So if we can show that p minus 1 and sigma n is co-prime, that if their GCD is 1, then p should divide 1, but p is a prime.
Right. That will be enough if that is true. The thing is, you can rig your thing to be. Okay, no, actually, that might be true. Yes, yeah. Actually, yeah. That works. Yeah. That works.
So
But
can
yeah,
you please explain a bit about that ordered roots and primitive roots?
right. So yeah, it's not necessary for INMO as such, but as you would go on to do more Olympiad math, Olympiad number theory, you would need these concepts. So orders and primitive roots are kind of tools that we use in number theory. So Order is, so suppose you have some natural number n and an integer a such that a is co-prime to n, then you know by Euler's theorem that there will be some m such that a power m is congruent to 1 mod n, right? The thing is, the least such m for which this holds, the least positive m for which this holds is called the order of a modulo n. Now these orders and order kind of has like some nice properties. With this notion of order has comes along with some nice results that you can use in many problems. What primitive root is, that is the, so if you look at things modulo p or modulo p power alpha for any prime power actually, and if you take any natural number, any integer that is co-prime to that p power alpha, then a primitive root is essentially an integer t such that this a will be congruent to some power of t modulo that particular prime power. So yeah, I think Ivan should have some notes about orders and primitive roots.
So could you repeat the definition of tau and sigma?
Yeah, so tau n is the number of factors, and sigma n is the sum of factors.
So in the question number 6, the last question, sir, is the answer f of x equals to x?
F of x equals to x indeed is a solution.
It should be f
the
of x
negative,
equals to kx.
not exactly kx, because then you have k square times x cube. plus
Sir,
y cube.
actually, I did it using calculus. Basically, first I partially differentiated it with respect to y, and then I put y equals to 0, and like that.
Yeah. The thing is, one thing you should know that about Olympiad problems. So unless you are given that the function is differentiable or continuous or whatever, you can't exactly employ those techniques, because the thing is, f is some random function from reals to reals, right? You don't know whether f is differentiable or continuous just yet. So you can't differentiate f.
Means we cannot use calculus directly if we are not.
No, you can. There's nothing stopping you from doing that. But the thing is, this is not entirely mathematically accurate that you differentiated f, because there are non-differentiable functions, right? Not every real function is differentiable. So you can't exactly use. You can't exactly differentiate the function without proving that it is differentiable. If you are able to prove that some particular functional equation implies this function has to be differentiable, then you are free to use it. Like, absolutely use it away. But the thing is, you can't directly assume that f is differentiable, so you can't differentiate it.
Sir, in number
Sir,
2, how can we show that p minus 1 and tau n are co-prime? Sir, because
yeah, so the thing is, this tau n has a formula, right, based on the prime factorization.
Yes, but sigma n can have a smaller prime than the smallest prime of tau n. Then we cannot get it.
Yeah. The thing is, you need to prove that it can't.
Sir, but
no, it can have a smallest prime factor, but the thing is that p minus 1.
Okay, but p minus 1 and sigma n cannot be co-prime if sigma n has a smaller prime than the smallest prime of tau n. Means it may not be co-prime.
Yeah, you need to think about this a little bit. I have mentioned the source, so you can actually go to the solution and check out. Yeah, I think you should think about this a little bit. So. Okay, so this is Ivan's notes on orders and primitive roots. So if people are already not familiar with it, they can read this thing from there. Although I would suggest that don't expect this to come in handy for INMO just yet. You can. There's no. You should always keep learning. So yeah, this is my sole reason for sending this is just for learning purposes, not INMO per se.
Sir, for the perspective of INMO, which countries' national functional equations we can do like that same level?
You can. The thing is, since you're doing your aim is to do Olympiad math, right? Not just get into IMOTC or qualifying more. So yeah, you should solve any problem that looks interesting to you. The Having said that, there's this collection of nice function equation problem that Amir has.
Yes, sir.
Yeah,
Amir Hussain Parvati has lots of
yeah,
problems.
yeah, yeah. So though he has this collection of 100 functional equation problems. Yeah, I'll I'll try to find it. Yeah. Um, it's on Amazon. It should be on his website as well. Yeah, I'm actually sending in chat these things. So, um, yeah. Okay. Yeah. So there's like he has some nice notes that you guys can refer to. All right. Any other questions? Yeah, somebody in the chat actually suggested plus minus x for, I would assume, problem 6. Yeah, that is correct actually. Plus minus x are the solutions. All right. Okay. So let's see. We have discussed 3, 4, kind of 5, I would say. Yeah, this is good. So yeah, I guess I can kind of write down about this second one. So right. So if you take n to be p1 power alpha 1, p power alpha r, tau n is just product of alpha I plus 1, and sigma n is just this product. Right. Um, Now, if you take the least prime factor of tau n, right? So p. Okay. We need to show that p does not divide 2 power sigma n minus 1. All right. So suppose p divides some alpha I plus 1. For p to divide pi power alpha I plus 1 minus 1 more by pi minus 1, you need to have that alpha GCD of alpha I. Okay, not p does not need to divide this. P does okay. So GCD of p minus 1 comma this thing. Right. So the thing is, you need to show that p divides. You need to show that p does not divide 2 power sigma n minus 1. Now the thing is, if you show that GCD of sigma n and p minus 1 is equal to 1, as the person in the audience suggested, then you're done, right? Because that would just imply order of 2 is 1.
Sir, but there is also a case that if p is equal to 2, then this does not hold. Means 2 power p minus 1 is not divided by p.
Exactly. So p won't divide it either way, right? So you can just like, so we are trying to show that p does not divide 2 power sigma n minus 1. So if p is equal to 2, then we are done right away. So we can just work with the case where p is not equal to 2. Now the thing is, if we can, so we have reduced the problem to showing that GCD of sigma n and p minus 1 is 1. Okay. Now suppose, so the thing is, you need to check that GCD of p minus 1 comma pi power alpha I plus 1 minus 1 mod by pi minus 1 is equal to 1 for all I, right? Because sigma n is just product of these. So now p minus 1 you have here. So suppose there is some common prime that divides. So suppose q divides p minus 1 and q divides pi power alpha I plus 1 minus 1 mod pi minus 1. All right. Okay. So then now alpha I plus 1 is a multiple of order of pi modulo q, right? Okay, times something. So essentially what I'm trying to say is that order of pi modulo q divides alpha I plus 1, or q divides alpha I plus 1. This is because of LTE, by the way. So uh, yeah, there's this lemma called lifting the exponent. Right. Okay. So yeah, somebody in chat actually asked about the solution file. So I mean, I guess I could send it to Sumana ma'am, but I don't. I'm not sure how helpful this would be. Like, it's kind of like it's not properly explaining anything. So yeah. Anyway, so yeah, you have so if suppose this happens, then you must have this thing happening or this thing happening. The thing is q divides p minus 1 and q divides alpha, but the thing is this alpha I plus 1 divides tau n. So then this would imply that q divides tau n, which would be a contradiction because q divides p minus 1 and p was the smallest prime factor of tau n. So this cannot happen. So you must have that this is happening. Now order of pi modulo q dividing alpha I plus 1. All right. Now this order thing, right? So you so then this implies that either order of pi modulo q is equal to 1, or the thing is this particular thing also divides q minus 1, which is less than p. Now if this was not 1, then this would have a prime factor that divides q minus 1, which is less than p, and this divides alpha I plus 1, which again further divides tau n. So what you have is that order of pi modulo q needs to be 1. Okay. Actually, the thing is, you can. Okay, I actually did not need to do all this. Okay, this is my bad, completely my bad. Yeah. Okay. Uh, okay, I kind of erased the entire thing. So anyway, doesn't matter. So yeah. Oh shit. Okay. uh, all right. So we had so what do you, so we had tau n is equal to alpha I plus 1 sigma n to this product of pi per alpha I plus 1 minus 1 more pi minus 1. Now you took p to be dividing alpha tau n, least prime factor, um, to show. So we were trying to show that GCD p minus 1 pi per alpha I plus 1 minus 1 not pi minus 1 is equal to 1, right? So suppose you took some prime q dividing p minus 1. Now you assume that pi divide this modulo pi minus 1. Now you can actually now you're directly done if you use LTE here. So the thing is, what LTE, this is lifting the exponent lemma. So what this says is that so suppose so q divides this, right? So you have that vq of pi power alpha I plus 1 minus 1 is greater than vq of pi minus 1. This is possible only if q divides alpha I plus 1, which further divides tau n, and this is less than p, which gives us the contradiction. Uh, so yeah, what this lemma states is that p is an odd prime, a belongs to z comma 3, p is equal to 1. Um, you have a vp of a power n minus 1 is equal to vp of a minus 1 plus vp of n. For p equal to 2, this is a similar statement, but there's some issue with when VP of n is equal to V2 of n is equal to 1. Okay, by the way, VP of n is the largest power of that prime P dividing n. So yeah. LT again is a standard result, so I guess you can look it up to find applications and such. Also, having said that, it being standard, sometimes while grading in most scripts, if students use LT without completely stating it, so some graders cut points off. So I think it's my responsibility to add that into this conversation as well. So if you are planning to use LT or any completely non-standard result in the contest, then you are expected to properly state the result and a source where you can find it. So suppose, for example, you are using something with LT, right? So you can just say that Ivan Chen's notes or whoever notes you studied LT from, you can just say that this guy's notes have that thing, and that's perfectly fine. But you need to state that particular result properly in your exam. Otherwise, you might lose some points. Especially in geometry, because people start using lemmas, some really powerful lemmas from Ivan's book, Left and Right Hand. Yeah, they have lost points before. So you need to state everything clearly. All right, yeah, I guess that was it. Any other questions?
Sir, I think I have a solution for the last question.
Okay.
So should
yeah,
I?
you can. Yeah, you are open to share it. Yeah.
Yes, sir. I am putting in the functional equation. I'm putting that. Uh, Firstly, we know that f of 0 should be 0. Put x equal to y equal to 0, and f of 0 comes out to be 0.
Yeah.
Know that. Next, we put y equal to x minus 1 by 2.
Okay.
So, sorry, not y equal to x minus 1 by 2. First, we put that f of x is equal to x times g of x.
Okay. All right. Uh-huh.
F of
So how do you define g of 0?
F of x.
Yeah. So the thing is, this will uniquely define fx for gx at all points except 0. Are you assigning something to g0, or like it's fine, like anything works?
And g0 anything works. G0
Okay.
we don't need to worry about g0.
Okay. All right.
So x is equal to 0. I'm not considering that case at all. Like that is why I found out f0 at the beginning. I know f0, so I don't need to worry about what the value of f0 is.
Okay. Sure.
Okay. So moving on, I am putting y. You will see that the equation like g of x plus y into g of x square minus xy plus y square is equal to 1, right?
Yep.
Yeah. So I'm then putting y equal to x minus 1 by 2.
Okay.
Then you'll see that x plus y comes out to be 3x minus 1 by 2, and x square plus y square minus xy also comes out to be 3x minus 1 by 2.
Is that so? That's interesting. Just let me calculate it for a second. So you are putting it y as x minus 1 by 2, right?
Yeah.
Okay. Just hold on a second.
X minus 1 whole by 2.
Yeah. That's not exactly true, right? Because the x squared term kind of stays, right? So if you have, so you will have x squared minus x times x minus 1 by 2 plus x minus 1 by 2 whole square. If you look at the coefficients of x squared in all these three terms, you will have 1 minus half and 1 by 4. So that won't give you 0. So it will have an x squared term.
My point is, I found out by this thing. I put x plus y equal to k. X plus y.
Yeah.
So my other term, x square minus xy plus y square, it is equal to k square
Yeah.
minus pxy, right?
Yeah. Um, yeah,
Uh,
it will be something. Yeah, yeah. Doesn't matter. Yeah.
a
Yeah,
square
that's actually the way to do it. So if you fix x plus y and you vary x like y as k, and you just plug in y as k minus x, and x is free to go over all real numbers, and now you just notice what values x square minus xy plus y square takes. So it
yes.
will actually be able to take every value beyond a certain point. So you have that f is constant beyond a certain point. Now the thing is, this particular point you can keep on shifting it.
Ah,
So therefore you just you have that this particular g function g is constant everywhere, and yeah, it has, and g square is 1, so g has to be plus minus 1. Yeah,
yes,
Sir,
that's right.
sir,
Hmm.
sir, I was also going through this process, but I found that the limit of x square minus xy plus y square gets to 1 by 4, no matter whatever x plus y we fix.
Wait, so if you fix x plus y to be k, so okay, let's just work this out then. So you have x square minus x times k minus x plus k minus x whole squared, right? So you have x square minus kx plus x square plus k square plus x square minus 2kx. So you have, okay, this gives us 3x square plus k square minus 3kx. Is the calculation correct? Please correct me if I make some calculation mistake. All right. So you have your k as fixed, and now you need to see where this goes. So what are you saying exactly? The limit going to 1 by 4?
I calculated using k equal to 1.
Oh, okay, okay. Yeah, so I mean, k is up for you to choose, right? So you can just choose k to be whatever.
Yes, sir,
So
just for
yeah,
example.
yeah, it's fine. So this just becomes root 3x plus what? Yeah, it's been really long since I've done this stuff. So um, root 3x times root 3 by 2k. So 3k square by 4. K square by 4. Root 3x minus root 3k by 2 whole square plus k square by 4. Yeah, so as you can see that this can take any value beyond k square by 4. Right. So the thing is, you have that fx is equal to constant, some constant c for all x greater than k square by 4. Now you can just take k to be 0 even, or as close to 0 as possible. So you have that fx is equal to c for all x greater than 0. Once you have this, um, you can directly put on large values of x and y, and you will get that the c square is equal to 1.
is it fx
Okay.
or gx?
Sorry, gx. Yes, my bad. Sorry, gx. So you have that c square is 1, so you can just assume c to be plus 1 or minus 1. It doesn't matter. So you just let c be 1. So you have gx equal to 1 for all x greater than 0. Right. Now the thing is,
Gx.
you had your gk times 3x square minus 3kx plus k square to be 1. Now you can fix k to be anything, right? Any real number r, and you can take x large enough so that this particular thing, actually this will always be positive, so this is 1 anyways, right? See, because this one was just root 3x minus whatever k by something plus k square by 4. So unless you have your k to be 0, you can just always assume, so unless k is equal to 0, this is positive, and once you have that this is positive, this becomes 1. So that just gives you that gk is 1.
Sir, how do you get the gx equal to c for all x?
For all x greater than 0, that is.
Yeah, but how do you get that?
Okay, so you have that uh, g of this thing times gk is 1, right? For all real x.
Yeah.
This is something that we had. So the thing is, then you have that this g of this particular thing is some constant, right? The thing is, since it is equal to 1, gk is not equal to 0, so it's 1 by gk. So we just take that to be C. It doesn't matter. We just take that to be C.
How do you know that covers the whole real number line?
Yeah,
3x square.
it doesn't. It doesn't. It actually covers everything beyond k square by 4, as we have calculated over here.
Oh, you can
So
take k square very small, so you can say
exactly.
x.
You can make k square by 4 as close to 0 as possible. So for all positive values you have your thing.
Sir, could you please once again show what we have defined as gx?
Gx was just fx by x. Gx is fx by x for all x not equal to 0.
So we are showing gx constant so that we can get fx is some kx, and from that we are getting it ks plus minus 1.
Yes, that is right. Yes.
Sir, I have a question. I have sent it in the chat. Can you
Okay.
kindly see?
Which one? This was the one that you privately messaged me?
Yes, sir.
Oh, okay. Yeah, I'm pretty sure you can do that. So, see, the function that you construct doesn't have any extra condition to be continuous or differentiable, right? So, you can just take some x. I mean, for each x, you can just take some x, and yeah. I mean, I don't think it should be tough to construct. I mean, honestly, I guess. Um, uh, right. Yeah, I'm not sure. Yeah, this should definitely be possible. So, okay, let's just work this out then. Okay, I think I'm out of time. So, yeah, this is supposed to be just 1 o'clock. So, yeah, maybe if I come up with something, actually, you know what? Just email me. So, I'll just send out my email if you guys
Sir,
have.
please send your email ID in.
Yeah, I'll do that. Yeah. So this is my email. Just write to me if you want any help. Yeah, I'll try this one. I'll try solving this. Yeah, but it shouldn't be tough. I think it should be easy to do so.
Sir, could you please tell the problem one time?
Yeah. So what he's saying is that it's a construction problem. So he's saying that we are trying to find a function f from R to R such that f of x is equal to x square minus 2 for all x. And his question is such a construction possible?
Thank you, sir. Thank you.
Yeah. So yeah, I guess I'll yeah. So yeah, I guess I'm done. Yeah, I think we can stop there.
Yeah, there are no questions, then we can end the meeting.
Yeah, if there are any questions, then please.
If there are, yeah. I guess there are no questions. Shubham, yeah, thanks a lot. And I think it's okay to end the meeting.
Yeah, definitely.
Soham, Soham, can you